This is by Yarden Shafir. Hello, Yarden.
Hello, how are you?
I'm very well, thank you. How are you? And where are you calling in from?
I'm good. I'm calling in from Greece right now.
Ah, lovely, excellent. And is that your artwork on the walls behind you, or is that?
No, this is not mine. This is the print.
Very good. Anyway, we are, well, we're in order to try and stay on track, we're going to crack straight on. You are going to talk to us about, and since I'm definitely not going to know what this is about, callback objects. Everything
Yes.
you didn't know you wanted to hook in the kernel. So, Yarden, please take it away, and I'll be monitoring for questions and get back to you at the end.
Yes, let me share my slides. Okay, let me know if that worked.
I think that's worked.
Good. We're good.
And I will leave you to get on with your presentation. Thank you very much.
Thank you. Okay, so yeah, like I said, I'm Yarden, and we're going to talk about callback objects. Is an internal communication mechanism in the Windows kernel that you're probably gonna want to use or look at for your next rootkit or EDR software. So first of all, about me. My name is Yarden. I'm a software engineer at CrowdStrike, previously at SentinelOne, doing Windows security, research, and development for mostly defense purposes. I'm also an instructor in Winsider, teaching Windows internals classes together with Alex Nesco. And I'm also a circus artist, instructor, and performer, mostly working in Israel, teaching and performing aerial arts. I do a lot of things. I'm a pastry chef, and during quarantine, I mostly taught my mom how to unmute Zoom almost by herself. So that's probably my greatest achievement so far. And what about callback objects? They might sound familiar to a lot of you because the Windows kernel has a lot of things that have the name callback in them. There's a lot of user mode callbacks, kernel mode callbacks. Some of you might know the process and thread and load image notifications, which are also called callbacks. Those are all different things. For example, process and thread notifications are legacy callbacks, which are different thing in which the kernel notifies different drivers about certain events happening in the system. Now, callback objects are a slightly different thing. They're an actual object, like a file, like a process, like a symbolic link. They're one of about 70 different object types in the system. And they're named. When you create a callback, you can choose a name for it or not. You don't have to. And that's how other drivers in the system are going to recognize it. And the thing that makes callback objects different from few other communication mechanisms in the kernel is that anyone can create a callback, anyone can register for one, and anyone can notify one. Unlike other mechanisms in which the kernel exports some functionality, some options, some callback, like here you can register to receive notifications about processes. With callback objects, anyone can use them in the kernel any way they want. There are certain callbacks that the kernel makes available, like power state, if the system is going to shut down or restart or go to sleep, and a few other things. But you can also create your own callback object. For example, if your product has 2 or 3 or 4 different drivers that want a way to pass information to each other, you can create internal callback objects, have all your drivers or some of them register for those, and any of them can notify the others to pass any kind of information you want. Callbacks, when notified, receive 3 arguments, 2 of them controlled by whoever is notifying it. So that's as long as all sides as long as all sides of the communication agree on which arguments these are, which types they're in, you can have your own internal communication mechanism inside the kernel. But it's not private. Anyone can register to any callback, almost. We'll see how that's not true and how it's still kind of true anyway. So this is roughly what that mechanism looks like. You have a few drivers. One of them creates a callback with exCreate callback. Creates a new callback object that they said can have or not have a name. And other drivers can register for that callback. To register for it, they first need to find it. They do it again with exCreate callback, which gives them pointer or a handle to the object. And then they can register functions. They can register functions that will be notified when someone wants to notify the callback. And then after there are registered drivers, any of the registered drivers can notify the callback, and anyone who registered a function will be called. Thing is, you can notify a callback without being registered to it. You just need to have the handle to the callback. Now, you're not supposed to have the handle without registering, because you're supposed to receive it when you register a callback function or create the callback. But you're in the kernel, you have access to basically everything, so you can kind of get the handle anyway by yourself. Here is some simple code, simple POC code to show how to create and register a notification function for a callback. In this case, it's the kernel's image verification info callback. That's one that's provided by the Windows kernel, starting in Windows 8.1, and that's a fun callback that gives you, for every newly loaded driver, information about its hash, its signature, its certification. So for an EDR tool, that's a fun one to use. As we can see, like with almost any object, we need to initialize the object attributes, part of which are the name of the callback we want. Then we call exCreate callback to get the object. And then we use that object to register our own function. In this case, I call it image verification callback function. And then every time a new driver is going to be loaded, the kernel is going to notify our callback and any other callback and any other function that was registered for this callback. Fortunately, the internal structures that are used for callback registration are not public. They're not documented, and they're not in the symbols, which makes callback objects a bit harder and more annoying to work with, especially if you want to debug them, because you can't use public symbols for that. But the structures are pretty well known anyway. We have two main structures that we need to know. There is the one on the right, that's the callback object itself. That's what you're creating and receiving when you call exCreate callback. It has a signature, which is not very interesting, and a lock. And then it has two linked lists. Personally, I like linked lists because that's the easiest way to get access to information that you might not normally have access to. When you want to find something in the Windows kernel, if it's not exported or some official documented thing, you might have a hard time finding it. That's why we have things like binary scanning, trying to match specific bytes and signatures. But if something is linked in a list, it's enough to have one part of the list to have all of it. You can just walk the list. So I like lists. In this case, we have two. The last field here is the callback list, which links all the callback objects in the system in a single list, which means once you have one callback object, you can find all of them. And the second is the list of registered callbacks, because when you register a function to be notified by a callback, you don't just register a function, you create a callback registration structure. That's what gets internally created. And we'll look at that in a second. And those are all connected by a linked list, which makes sense. Kernel needs to have a way to get all the registered functions and notify them one by one. So a list is an easy way to do that. And the last field in the callback object that's interesting is allow multiple callbacks. Like the name suggests, that's Boolean value that says, do you want to allow more than one callback function to be registered here or not? That field is being specified when the callback is first created. And if it's set to false, when you register a callback function, the kernel will check if there's already someone registered for this callback. And if there is, it won't let you register. Now, that's not a very major limit because the callback is in the kernel, your driver is in the kernel. You can go and patch the list yourself and just add your function there anyway, but you're not supposed to. So now when you register a function for a callback, behind the scenes, there's a callback registration structure that's created. Again, that has the linked list connecting all the callback registration structures. It has the pointer to the callback function, and it has a pointer to something called a callback context. Now that callback context is, let's see if I have that. No, in my example, I didn't use it. That callback context is a pointer that you supply when you register for a callback. And whenever the callback is notified, every function that's listed in the list is going to be called and receive as one of the arguments the callback context that it registered. It's not something like the caller, it's not something that whoever notifies the callback determines, it's not something that the kernel determines. Whoever registered the callback will receive its own callback context when the callback is notified. On first look, that might not make much sense because why would you register an argument that you're going to receive later? Actually, that's the logic behind is that this is a pretty rough way to implement classes. The kernel is not built with classes. It's basically C. There's no complicated development concepts there. There's no classes in the kernel, but that's a rough way to implement a class where whenever the callback object is notified would receive the class instance. Basically, it's a way for drivers to have some internal global data structure that they want to have available in a lot of cases, including in their callback functions, but without saving it as a global that anyone can easily find. So that's that. And why is that interesting? Because that means that those callback contexts, when used, will probably be pointers to pretty large internal data structures where we might have information that we're interested in, but we'll have a pretty hard time finding otherwise because it's usually pool memory. It can be anywhere. It doesn't usually have something that makes it easy to identify. To find it, you need to go and dig inside the driver for pointers. But the callback context is an easy way to find a pointer into it. A lot of drivers don't use that callback context. Later, we'll dump some callbacks and see, and mostly it's null. But when it's not, you can sometimes find some interesting things there. Here, we basically have the same thing in diagram form. We have the two lists. We have the list that connects all the callback objects together. And in each one of them, we have the internal list connecting all the callback registration entries inside the callback. Each callback registration is one driver that registered a function to be notified when the callback is notified. As we can see here, if we get one of them, any of them, a callback object or a callback registration, we have all of them. We can find every registered function in every callback object in the system. Means even if there's callback objects that we can't easily find, for example, unnamed ones that we can't index by name, we still have a way to find them. Now, who actually uses those callbacks? First, the Windows kernel itself exposes some callbacks, like a very popular one, a pretty well-known one, is the power state callback I mentioned earlier. There is a processor add callback. There's a licensing data callback. And like we saw the image verification one, that's pretty useful for EDR software to know what drivers are loaded. One thing I have to add is that callback objects are, unlike some other parts of the system, callback objects are just notifications. For example, being notified that a driver is being loaded doesn't give you the option of blocking it or changing it in any way. It just sends you a message saying, hey, this thing is being loaded. Here's its information. Good luck. So there's a few of those. There's some interesting callbacks in the kernel that some of them are used pretty often. For example, Win32k has some callbacks that uses mostly anonymous callbacks for internal Win32k communication. And for whoever is interested in Win32k exploitation and bugs and finding more ways in there, that might be an interesting direction to look at. Other than that, there are security products that use them for internal communication. Security products that have more than one driver and want an easy way to synchronize between them and pass information might use that. For example, Windows Defender has a few different drivers and uses callback objects for communication between them. And it's actually a fun example to look at that we'll look at in a bit more detail later. And another example that's pretty interesting is patchguard. Patchguard has a callback object that is used to initialize a pointer to a function that does patchguard periodic checks. And we'll look at that a bit more later too. Now, I'm mentioning all these callbacks, but how can we actually find them? These callbacks, because they're not just the kernel's callbacks, because anyone can use them, each of you will have different callbacks on your system based on what products run there. Like, is Windows Defender running? Or do you have some other security product or some other things that use callbacks? So, few ways to see what callbacks you have. One of them is using WinObjX. That's a pretty easy one, just looking for callbacks with WinObjX. The only limitation is that it's only going to show named callbacks. It won't show you the unnamed ones. So you'll only see ones that have a name. Another option is to use WinBag and run bang object /callbacks. I'll show this later when I show the demos. But that, again, that will only show the named callbacks. You can also use WinBag to write a script, a DX script or a JavaScript script to manually parse the callback objects, and then you'll have all of them, not just the named ones. The part that makes it difficult is, again, the internal structures are not documented and not in the symbols. So you'll have a bit of a hard time doing that. It is possible, but it will be slightly difficult to work with undocumented structures in WinBag. Third option, which I'll show later, is using C, writing either debugger API, which is what I did, or writing a driver that will parse the callback list. Both are valid options. I wrote a tool to do that, a debugger API tool that I'll share later. And then if we look at the list, this WinObj EX screenshot is from my machine. And we can see stuff like that first one, the one with all the weird named number. That's the patchguard callback, actually. Then we have all sorts of callbacks from my audio and video cards. There's a few of them here. We see the power state callback. We see the image verification callback. And at the end, we see 3 WD callbacks. Those are the Windows Defender ones, the ones that Windows Defender uses for its internal communication. Now we've seen this mechanism, we see what it does, we see how we can legitimately use it. How can we abuse this mechanism? Now there's all sorts of fun ways. Like I said, this mechanism can be used for internal communication, but it is not private. As long as a callback is not defined with don't allow multiple callbacks, anyone can register to it. You cannot specify who is allowed and who is not allowed. Even if technically a callback is not allowed to have multiple callbacks, you can go and patch them and patch the memory yourself. You can find pointers and hook communication by replacing the pointer with your own function, or just adding another one to the list and listening into callbacks that might have interesting information that we want to follow. For example, the Windows Defender callbacks. You can also remove functions from those lists, which will probably break something depending on what you remove and from which callbacks. You can use the callback context to find pointers to interesting structures, interesting internal structures used by drivers that you care about. And you can also notify those callbacks yourself with possibly false information, which could, with security products, which could lead to some interesting results there. Well, a couple of the examples that I mentioned that we'll look at are Windows Defender and patchguard. So Windows Defender, a very rough design it has is Windows Defender on Windows 10 has 3 drivers. First one is the filter driver, which does a lot of the work. It registers for the process and thread notifications. It monitors file system, does all sorts of things. That one has 1 callback. The second one is the network driver, which communicates with the management system, and that one has a 2nd callback. And the last one is the boot or ELAM driver. For anyone who's not familiar, ELAM is a Microsoft program in which it allows certain AV vendors to load their driver very earlier than most drivers are allowed to load. And what those drivers are allowed to do is pretty much one thing: register for Windows callback, another callback object, which will notify them every time a boot driver is loaded with information about the hash, with some basic information about the driver. And this one allows the AV driver to use an allow list or block list to decide if it wants to block those drivers. That's meant to allow some AV drivers to block early loaded malicious drivers like rootkits that will be loaded in the system. So Windows Defender has a boot drive, has an ELAM driver that is loaded very early in the system, registers for this callback, and has an internal callback object of its own that it uses to communicate with the filter driver. So what does this callback do? One thing to know about ELAM drivers is that they have to unload early too. They're allowed to load very early, see all the boot drivers load, block or not block them, and then they need to unload. They can't keep running. So what the Windows Defender driver does is that it receives those driver notifications and it saves the information about the drivers in an internal data structure. Then when the filter driver loads, right before the boot driver needs to unload, the filter driver registers for the Windows Defender boot callback and notifies it, telling the boot driver, hey, send me all the driver information that you kept. So it can use it for whichever detection logics or notifications or whatever it wants to do with them. And the boot driver sends back that internal data structure with all the information about their early loaded drivers. So that's one callback, which is if you manage to load early enough before the boot driver is unloaded, you can notify that callback and receive all that information too, assuming you know how to parse it. The second callback is the filter driver callback. That's the call. We had it here. That's the last one on the list. The boot driver callback is the WDEB notification callback, and the filter driver it creates the WD process notification callback. So like it sounds from the name, the WD process notification callback is a way for Windows Defender to notify other drivers about processes starting in the system. Because what happens is the filter driver registers for the legacy process notification callbacks, the one where the kernel notifies drivers about every loaded process. So Windows Defender receives that notification that a new process is being loaded. It does some analysis, gets some information about the driver, and then it wants to pass that information to the network driver so it can pass it on to the management server, to the centralized server. So when Windows Defender is notified about a new process, it gets whatever information it needs, it saves it in its own internal structure, and then it uses the Windows Defender callback object to notify the network driver, hey, there's a new process in the system, here is the information about it. Now, what's fun about this callback is that something that I haven't really mentioned before, callback objects are not very well known. And as far as I know, they're not really monitored by anyone. I don't know any security products that monitor them. Tools like WinCheck don't dump callback objects as far as I'm aware. So they're not really looked at. But for example, the legacy callbacks, the legacy process notification callback is a much more well-known one. And a lot of products are looking at it, seeing who is registered there. Where does it point? Does it point to driver memory? Does it point to non-driver memory? If you register there, you're a lot more exposed. But you can do something interesting if you have Windows Defender running and you want your rootkit to get process notifications, but not be super out there about it. You can let the Windows Defender register for process notifications, let it receive the data, process the data, and then register your own driver to the Windows Defender callback. So whenever a new process is loaded, Windows Defender will notify its own callback, and as a result, will notify your driver too. And not only do you get to sort of hide and not be super visible because you're not registered to the system's process notification callback, you also get slightly more processed information and kind of letting Windows Defender do some of the work for you. And the only downside here is that Windows Defender uses an internal data structure for all of its information, so you'll need to figure out how this data structure is built and how to parse it properly. Once you have that, you've got everything. And that's actually the most interesting callback that Windows Defender has. The third one is the network drivers callback, which is only actually called once. It's called when the network driver starts because it starts a lot later than the filter driver. When the network driver starts, it registers for this callback object that the filter driver creates to notify the filter driver, hey, I'm up, you can start sending me information. And then immediately the filter driver sends it the information about all the processes that were loaded before the network driver started. So it's only actually notified once. You don't really get different information than you do with the process callback. You just get you get information about more processes, but you don't get actually different information. That's just an internal synchronization mechanism for them. So the second callback object that seems pretty exciting is the patchguard callback. It has this very unclear name because it's not going to be called patchguard notification callback. And that one is also only called once. It's not called to trigger patchguard checks. It is called to initialize a pointer to the function that performs patchguard checks. The kernel notifies this callback once when initialization of the system ends, when phase 0 ends. The system wants to make patchguard start running, to enable patchguard, because everything is where it's supposed to be, everything is initialized. Now it wants patchguard to start monitoring. So it enables patchguard, and as part of that, it notifies that callback, which has one registered function to it. That function is in mssecflt. And it notifies it with a pointer to the function that will perform random patchguard checks. To tell mssecflt, this is the function that you need to call to do patchguard checks. Now, the interesting thing about this is registering for this callback is not very useful because you're going to register too late. If you somehow manage to have your driver running before phase 0 of system initialization ends, there are more interesting things you can do than registering for the patchguard callback. So registering for it is not going to be very useful because it won't be called by the time your driver is up. But looking at the way it's implemented, the function in mssecflt is implemented in such a way that it initializes its own global with the pointer that it received, but never checks if the global is already initialized. Which means if you notify this callback again, you can replace the pointer. You would expect it to bug check because, hey, the pointer is already initialized, who's trying to change it and why, but it doesn't. So you can notify the callback again and see what happens. Now, my guess is that on newer systems with HyperGuard, this pointer will probably be protected and you will probably not be able to change it, but it might be worth checking, might be worth seeing what's there. And also, if mssecflt is still registered for the function by the time your driver is up, it probably won't be, you can walk the registered the callback registration structures to see who's registered, receive the pointer to the callback function, do some simple binary parsing there. It's not a very large function, and find the global, which has the pointer to the patchguard function, the patchguard monitoring function, which is fun for some patchguard research. If you want to do some patchguard research. Obviously, this is a very rough description of callback objects. We only kind of scrape the surface here. There's a lot more interesting callbacks to look at. I would look at security products. I would maybe look at some other third-party products that might be using them. There is a base for some very interesting research here that can go in a lot of different directions. But what doesn't really exist is an easy way to investigate callbacks, like public tools or whatever. So let me unshare and share a tool that I wrote for this. Okay. So I wrote this simple tool that analyzes a crash dump or takes a crash dump of its own or connects to a kernel debugger and dumps all the callbacks and registered functions that are in it. So we'll let it run, and while it runs, we can look at things. So the first ones on the list are, as you'd expect, the kernel ones. There's enlightenment state, set system time. Here's the power state one. We see it's popular. There's stuff registered here that you'd expect to see in a power state callback. There's ACPI. There's HAL. There's a lot of other drivers here registered for that one. Now here we start seeing different callbacks. We see different. Here's, for example, one of the Win32k callbacks. We can see that it's unnamed. Win32k uses anonymous callbacks for its port signaling. Here's our few who chose the name null for the callbacks. Those are, I think, my graphics drivers. Here's the DAM driver, which always has some interesting stuff. On this machine, I don't have Windows Defender running, so we won't see that. And just because we have a couple more minutes, I'll show how we can also dump callbacks with Windbag, but only named ones. So simple, we run bang object. And give it a minute because always a bit slow. Internally, it just looks for all objects that have that part of that have /callback as part of the name. Now, while it's running, right? Never remember if it's one or two. So while we're letting it run, anyone has any questions?
So we don't have any questions yet, I'm afraid, Yarden. I think you've blown them away with your technical expertise, and
need some time to process.
Exactly. And I can tell you, as an ex-CISO, one of the great advantages of being a CISO is you get this very high-level view of everything that's going on security-wise in the organization. The downside of being a CISO is with this very high-level view of the organization. I didn't understand a word of what you just said, but but I do know that there are many people in the audience who will have found this incredibly useful. And folks, if you're still processing, not quite ready to ask Yarden a question just yet, you can still use the Slack channels. Yarden, you'll be on Slack, available to answer any questions that are sent your way. Please do continue the conversation afterwards. Having someone like Yarden with such a deep level of technical expertise here is invaluable to you. So please take full advantage and really, make the most of it. Let me just check time. We do have a couple of questions now. Typically, they've literally just appeared. So let me just check to see, do we have time? We've got 4 minutes to answer questions. So yes, thank you for getting the first one. But do you have any interesting structures in the object context that you've seen?
Yeah, and I'm assuming you mean the callback context there. So yes, if I'll reshare the output of the tool I wrote. It's on GitHub. I'm going to publish it later. And I'll send the link. Okay, so yeah, we have context output here. Yeah, we have the callback context output here. You can use it to see which functions have initialize a callback context and which ones do not. Like here, we see that doesn't. And one specific one that I know, if you're interested in graphics drivers, almost all the graphics and audio drivers do use a callback context, so there are probably some interesting stuff there. They're all pointing to very large structures. And the Windows Defender driver uses a callback context for all of its callbacks. And that points to the internal Windows Defender global data structure that always has interesting information of all sorts of different kinds, depends on exactly what you're interested in, but you're probably going to find it there.
Okay, excellent. And I think we do have time for the second question. What should you look for when Windows Defender is stuff and admin cannot start it anymore?
I'm not really sure what the question here is.
When Windows Defender is stopped, maybe? An admin? I'm not sure. Here we go.
I think that would be a question for the... Yes.
Oh, no, hang on. We've got a...
No, I think that would be a question for the Windows Defender technical support, which I don't really do.
Okay. And in which case, let's go on to this final question. What is the difference between the image loader callback object and the regular load image notify routine?
There's actually no image loader callback object. The load image notify routine is the legacy callback that notifies about newly loaded image. As far as I know, there's no image loader callback object. If you mean the image verification information, the difference is that the image verification callback is only for kernel mode images. It only notifies about drivers and it supplies information. That's actually a public one. All the structures are public because it's meant to be used by EDR software. And that gives you information, for example, about who signed the image. It gives you some information that you don't get from the load image notify routine, but they're used for separate purposes because one is only for kernel mode images and image load, and the legacy image load notify routine is for both kernel and user mode.
I hope that answers your question. So, Yarden, thank you very much. One of the huge downsides of a virtual event is that you don't get a round of applause at the end. So please take mine for your presentation. Please hang around on the Slack channels afterwards, folks. Please ask questions there. Yarden, you'll be posting links to the GitHub that you mentioned to Slack.
I will. Yes, I'll be posting it there and on Twitter. And even after the Slack channel is not relevant, it's easy to find me. Feel free to ask questions if you think of any later.
Fantastic. Do you have a Twitter handle or anything that people should know about?
I do. It's Yarden Shafir, the same name that's on the slide, so very easy to find.
Okay, excellent. Yarden, thank you very much.
Thank you.